Section 10.5, finding probabilities of independent and dependent events. All right, where have we come from? Well, we've looked at how to come up with various number of ways to count items. We've talked about permutations, we've talked about combinations and how permutations rely on an order, combinations do not. And those counting principles would have been like groups of items. Then we introduced probability, generic probability, and talked about experimental probability and theoretical probability. We introduced the complement. We talked about odds. And then we explored our compound events. What happens if you have a situation where you're doing some event A or event B and the probability of those two happening. And then finally, now we're at the independent and dependent events of probability. So, some independent events. Two events are independent if the occurrence of one has no effect on the occurrence of the other. And they give an example here. For instance, if a coin is tossed twice, the outcome of the first toss, being heads or tails, has no effect on the outcome of a second toss. So, they are independent of one another. And when you have independent events, as with dependent events here, we'll see in just a little bit, this is when we're going to multiply our probabilities together. Probabilities of event A and B equal to probability of A times the probability of B. All right, some other examples of this might be if I roll a six-sided die, and what would be the probability that I would land on a 6 3 times in a row. Every time I roll the die, I have a probability of 1 over 6 of landing on a 6. And the second roll that I make, the probability of that second roll is not affected whatsoever by the probability of the first time I roll the dice. So they're all independent of one another, giving me a 1 over 6 times a 1 over 6 times a 1 over 6. And that would be another example of independent events. Let's look at some other ones here. Some experimental probability here with a survey of males and females and asking what their favorite choice of ice cream flavor is. So here we have a 50 out of 75 males prefer chocolate ice cream. 40 of 50 females said they prefer chocolate as well. Now we go out and we randomly select one male and one female. What would be the probability that both of them favor chocolate ice cream? So again, going with generic setup here, we're going to just say generic probability of a male and a female liking chocolate. Would equal the probability that a male likes chocolate times the probability that a female likes chocolate. So what would our probability of males? Well, we've got a total here. 125 total persons interviewed, but we just want males liking chocolate. We know that there is a 50 over 75 chance of that happening. Females, out of the 50, there were 40 of them that liked chocolate. And these two can both be reduced, so we can become 2/3 and 4/5, and then get 8/15. So there's my probability that one male and one female randomly selected both like chocolate ice cream. 46% of parents say that they read to their kids at least once a week. If three parents are randomly selected, what is the probability that they will read to their kids? They'll say that they read to their kids. Going back to the ice cream example for just a second. Me asking a male and him saying yes or no, I like chocolate ice cream, has no bearing on me asking the female if she likes ice cream, yes or no, chocolate-wise. So those would be independent events. And here's the same thing. I just randomly go up to parents, and what one parent says will not determine the outcome for what another parent says. So this, again, is an independent event. And we say probability that 46%, well, that 3 parents read to their child Three sets of parents read at least once a week would be the probability that the first set of parents do times the probability that the second set of parents do times the probability that the third set of parents do. Again, we've got an and situation here. So another way of writing three sets of parents read, what about the probability of saying parent 1 and parent 2 and parent 3 read to their kids at least once a week? So that's what's going on over there. 46%, well, we don't know the numbers, but we know percentage-wise that it's just 46 over 100, and we're doing this 3 times. And this would simplify to about 0.097 after we multiply that all out. Make it a decimal number. So there's that probability that those independent events will happen. Well, sometimes we have situations that lend themselves to complements, and we've already talked about a complement as being equal to probability of some event not happening is equal to 1 minus the probability of that event occurring. And again, we looked at these phrases at least and at most, and how these could be potential setups for use of a complement. So here we have a 5-day period, and over this 5-day period, an employee is randomly given a 1 of 10 prizes. All prizes are available each day, and one prize is a $500 gift card. What is the probability that an employee receives a $500 prize at least once? All right, so we're offering the same prize 5 times in a row. So we're all 10 prizes 5 times in a row. So what we're looking for is a probability of $500 at least one time. In 5 days. And that'd be the probability of on day 1 we win it, and then day 2 we win it, and day 3, and day 4, and day 5. Well, what about looking at complements and saying that the probability of a $500 prize at least once in 5 days is the same thing as 1 minus the probability of not winning the $500 at all, any day. All right, let's look at that component. Let's take a look, first of all, at what is the probability of not winning the $500 in a given day. Well, there are 10 prizes, and one of those is a $500 prize. And so that means there are 9 of them that are not the $500. So in any given day, I have a 9 out of 10 chance of not winning the $500 prize. But that's just per day. What we want to look at is that this is happening over the course of 5 days. And so here we take day 1, day 2, day 3, day 4, day 5, and in each day we have a 9/10 chance of not winning it, the $500. This becomes an and situation, not winning on day 1, and not winning on day 2, and not winning on day 3, and so on. So these just become multiplication because this is an independent event here. But another way of writing 9 over 10 times itself 5 times is just saying, let's use an exponent, 9/10 to the 5th power. So here, what's the probability of not winning that $500 prize on a given day? Here we see the probability of never winning the $500 prize, which is what we are after in this part of our complement. All right, so we can go ahead and finish probability of $500 at least once would equal 1 minus the probability of not winning it at all, which we said was 9/10 to the 5th power, and this became 0.41. Or again, we could express percentage for probability as well. All right, so there we go. Situation where we have the same probability occurring over multiple periods of days. And what made this so useful in terms of a complement is the fact that we had opportunities to not win it at all 9/10 of the time. So the at least setups, these phrases at least, maybe think about using the complements. It's a lot faster. All right. Let's take a look now at our dependent events. So now, dependent events. Two events A and B are dependent if the occurrence of one affects the occurrence of the other. The probability that B will occur, given that A has occurred, is called conditional probability. And this is the notation that we use to represent conditional probability. It basically means the probability of event B occurring given that A already has occurred. And so you see in our formula down here for dependent events, the formula looks the same with the exception of the conditional probability piece at the very end. All right, so dependent. This would be your reaching into a bag of marbles, pulling out a marble. Now, what makes the event dependent? If I ask the first person to pull out the red marble, or a marble, and it happens to be red, they hang on to the marble. I walk the bag over to a second person, and I ask them to pull out another marble. Now, that second person, probability-wise, of drawing out a red marble or any other color will be affected by the fact that the first person has removed one of the total marbles that were in the bag. So now the total number of outcomes has reduced by 1. Thus, the second person's probability has been affected by the first marble being drawn. Now, had the first person drawn the marble and then placed the marble back into the bag, then I walk over to the second person and ask them to pull out another marble. Now their total outcomes is the same as the first person, and therefore that would have been an independent event. So here we have dependent, and we hold on to something, don't put it back, and we've changed our total outcomes. All right, we got a table showing status of 200 registered students. What is the probability that a randomly selected student, A, is a female? All right, now this is just generic. Again, this is experimental probability because we have this data here. But this is just generic probability. What is the probability that this student out of this group of students is female? So don't overthink this one. We have number of females over the total number of students. Females, 200 students, and divide each of them by 20, and we get 6/10 or 3/5. Okay, then though we get to the second part. What is the probability that if a female, that student is a full-time student? So this then becomes the conditional probability. And in this case it's, well, we want a full-time student out of the group of females. So that would be my probability notation that I'm going to use here. Well, I should rephrase that. We want a female full-time student is what we're looking for. Okay, So if we want a probability that student is female and a full-time student, that means we have the probability of the student being female times the probability of the female that is a full-time student. So here's the condition, and we go, we've already figured that part out. Now let's take a look and think about how do we come up with the second part, because there are a couple different ways you could look at this and interpret total outcome. So I want full-time students, and I want that full-time student to be a female. So maybe some people look at the problem here and determine that that conditional probability would say, let's take a look at all of the females, both part-time and full-time. That would be 120 total. But I don't want to consider part-time students. I only want to consider full-time students. So the full-time students becomes my total outcome, meaning out of my full-time students, male and female, I have 60 total full-time students, and I only want out of that full-time group a female. So this becomes a 40 out of 60. And then we reduce everything 3/5, and then we get 2/3, and that reduces to 2/5. There's my probability that we will have a female student and that female is a full-time student. So just be aware of your conditional probability. This is what I'm looking at for total outcomes. This F is my favorable in this case, what I want out of that group. Again, that's how I will think about setting up these conditional components. Right, so total outcomes is that part of the conditional notation, and favorable, what I'm after, would be the second component there. All right, so here we go. Take a look, and we'll determine whether or not we have some dependent or independent events. Given the fact that we're going to randomly select 2 cards from the standard deck, what is the probability? The first card is a heart, and the second card is a club if the first time we replace the first card, the second time we do not. All right, so if we're going to replace, anytime we have replacement, that means you have independent events. And then when we don't replace, we have dependent events because we've changed the total outcome. All right, so we have, let's see, our probability of a heart and a club. Well, that's going to be equal to the probability of drawing a heart times the probability of drawing a club. And the probability of drawing a heart, there are 13 hearts out of the 52. And we put the card back. I go to the second person, or I just draw again myself, and I have, again, 13 clubs that are out of the 52 total. And here I reduce. And we get a 4th times a 4th, or 1/16. Okay, now let's not replace. So I want the same thing. Probability of a heart and a club. But this time, this is dependent. So the probability of a heart times the probability of a club, given that I've already drawn the heart. Again, all that's being affected in this example is your total outcomes. Sometimes, like if I drew a heart and then another heart, well then both my favorable outcomes of hearts and my total outcomes would have been affected. But this time it's just the total. So 13 out of the 52 for hearts, but now I have 13 out of only 51 this time for my clubs. And then this reduces again, and we get 13 over 204. So that's dependent. All right, on this last example here, you and your friends are choosing from 8 different ISPs, internet service providers, and you're randomly selecting your own. So you don't know what either of your friends are picking. They don't know what you're picking. So let's just assume this all happens at the same time. You all get on the phone and you're calling at the same time to pick an ISP. And what is the chance? What are the probabilities that you would all choose different ISPs? So the question is this independent or dependent? And I guess you would answer the question by, I made the statement earlier that you don't know what your friends are choosing. They don't know what you are choosing. So in this case, if you just happen to randomly select, and it just happens to work out that you pick all different internet service providers, this would be a dependent event because of this. So we want the probability that you and friend 1 and friend 2 pick different. ISPs. That's what we're looking for. And I've suggested that we take a look at this as a dependent event. And the reason why is if I look at it as an independent event, the independent event would state that my total outcomes doesn't change. And my favorables don't change. In this case, though, we're looking at the fact that my favorable outcomes will be affected, because if I want everyone to have a different service provider, then that number that represents the number of possible internet service providers for myself, for my friend, and my other friend would have to change. It can't stay the same. So in this case, I've got myself. Let's talk about the fact that I have 8 choices. And I have the luxury in my example here of saying, okay, I'm going to be the one that gets 8 choices out of the 8 that I can pick from. All right. So I have an 8 out of 8 opportunity to pick a service provider. And then friend number 1 comes along. Now, they don't know it, but they only have 7 to choose from. And the reason they only have 7 is because, again, we want us each to have different ISPs. And so if I just did 8 times 8 again, or 8 over 8 here for friend number 1, that wouldn't account for the fact that we have different ISPs. So I have 7 out of 8 that my friend number 2 or friend number 1 gets to choose from. And then I have friend number 2. And again, we're assuming that they don't know, but they have, in order for all of us to have different ISPs, they have a 6 out of 8 chance of getting different ISP. And I know what you're wondering. You're wondering, well, why, after I take an ISP, would not my friend's total number on the bottom become 7, and then the second friend becomes 2? Again, I'm assuming that we are independently doing this at the same time, but we're looking for that opportunity, that probability where, what if we all happen to choose different ISPs? And so the number stays the same here because that's how many ISPs there are to choose from. The number changes up here because we each want a different ISP. And so we multiply this all together. What do we get? We get about a 0.5 41. So we get an 8 times a 6 times a 7. 336 divided by 8 to the third, which is 512. And I forgot to include friend number 3. Not so friendly on my part. All right, so oops. Friend 1, friend 2, and friend 3. Apologize there. We're going to have to add on here friend 3. So friend 3 gets included in the mix and has a 5 out of 8. So then we get back to what we're doing. 8 times 6 times 7 times 5 this time. So 8, 7, 6, 5, 1680. And then our 8 to the 4th, 4096. We can reduce that, and we get about 0.41. All right. There we go.